Good day. My name is Andreas Danner Nilsen, and I work as a software architect in a company called Arm. A few years ago, Professor Rakesh asked us in the industry what we needed from a low-level programming course. And since I had some opinions on that, I was then asked to hold a lecture on the subject. This is that lecture. I hope this will be interesting to those of you who want to keep working in the low-level programming world, either picking that as a career or as a hobby. Before we start, I kinda need to talk a bit about my company. So about that, that's part of the deal of doing a From the Industry hosted talk. Arm is a CPU company, and we are making a ridiculous amount of CPUs every year. That's because every electronic device ever typically has an ARM CPU or 3 in them, and that includes your PC. You probably heard about the big PC CPU producers like Intel and AMD, but you may not even have heard about ARM. So we are a hardware company, but we don't actually make any hardware. Instead, we make blueprints, or RTL, for customers, that's the SI partners on this picture, who then take those blueprints and incorporate them into larger chip designs. This earns us a very small amount of money per CPU sold, but as you can see we sell them in very large numbers, so it adds up. For us this is a good thing. We don't have to deal with all the fabrication nonsense and expensive factories that constantly need replacing every time a new fabrication technology emerges. And for our customers, this is also a good thing, because they get shelfware, CPUs and other chips that they can just take and incorporate for a very reasonable price, which is typically far less than they would have to spend by designing it themselves. Here in Trondheim, we make the Mali GPU. That's a graphics processor unit, if you don't know what that is. You probably heard about NVIDIA and maybe even AMD for the PC world. These desktop GPUs can easily consume a full power supply worth of power on its own, and the power supply typically delivers up to 750 watts of power. So that works in the PC world because you have big ass cooling systems to cool down these GPUs. You probably even heard them working at full power inside your desktop if you have one. In the mobile world, these GPUs don't work. They just use too much power. A mobile phone has a power budget of around 3 watts. If it uses more than 3 watts, it will get too hot in your hand and you will burn yourself touching it. So out of these 3 watts, a GPU can't use all of it on its own, and typically we have to make do with, say, a watt. That doesn't mean that a mobile GPU is 750 times weaker than a desktop computer. It just means that we have to be very careful about designing our hardware and software so that it doesn't use too much power. The Mali, that's Croatian for small, is a low-power GPU designed for chips that need low power consumption or just be very, very cheap. Obviously this is designed for cell phones, yes, but it's also used in other devices that want a cheap GPU, that being cars or printers or television sets. There's even devices I don't even know what's being used for. You may not even have heard about the term microcontroller yet, so let me start off by rehashing that. Microcontroller, or an MCU, is essentially just a small computer. It's got a CPU on it, it's got some RAM on it, got a system bus on it, and it has various other things like a program storage, which typically contains a read-only memory of all the instructions this microcontroller is supposed to execute. The main difference from a PC is primarily the performance. This is weaker than a full PC, but in return it uses far less power, and that means it generates far less heat. Since it also has far less transistors, it means it costs less to produce. And that's where the trade-off is. This microcontroller here is really cheap. Now, the downside is, of course, you can't really connect a keyboard and mouse to this. That's where you need a lot more connectors and integration into the system if you want to do that. It's possible though, but it takes a little more effort. So the fun thing is, the image I showed you in the last screen isn't really even the microcontroller. The microcontroller is a small wafer of electronics tucked into the casing I showed you on the last slide. You can see it at the bottom of this slide here, the wafer itself. This wafer is just done using whatever fab technology it was designed with, but it's essentially containing the CPU in one region, RAM in another, program memory in another region, and so on for every single thing that this chip is doing. Comparing a PC to an MCU is fairly fun, but it's not really a fair comparison. If you look at the specs, the PC is blowing the MCU out of the water, as it should be doing, costing about 1,000 times more. But that doesn't mean the MCU is useless. It's weaker, yes, but it has a far better power story. You can build a chip connected to a battery that can literally last you years without changing the battery, whereas the PC just dies a microsecond after somebody cuts the power to it. And just because it's weaker doesn't mean it's bad. You can compare this MCU here to the Apollo Moon Lunar Landing Computer, which is a far worse piece of computer that actually managed to land us on the moon. So you can do a lot with an MCU. It's just constraining to have to work with a weaker computer. It's not a blocker. You can land on the moon with this MCU. So I like to think that small is awesome. This is one of my favorite projects, as a guy that took one of the MCUs that I showed you earlier and designed a small connector board to it that has, well, essentially buttons and power, and just connected that together and made a small handheld gaming keychain. It's all you really need is a little hobby enthusiasm effort, and everyone in this auditorium can do. No, I'm not in an auditorium right now. Anyone in this class can do the same thing. So if you want to play around with a microcontroller, do so. It's not really that hard. There's a lot of aids that can get you started, the biggest one being probably Omega Verksted here at the campus. So if you feel this is fun, go for it. What I will talk about today is programming for MCUs. Let me start off with the claim. You may agree with that claim or not, and the answer is, in my opinion, subjective. My claim is that low-level programming is a mental state of mind more than anything else. Doing quotation mark good low-level programming is not so much about which language you use as it is about the mindset of the programmer. You can do pretty darn great low-level programming in JavaScript, just as you can do pretty horrible low-level programming in raw assembly. What matters isn't really the language, what matters is the mindset. When you program low-level, you will constantly keep in the back of your mind, does this implementation fit my platform constraints? And adding up 1,000 such small considerations is what makes the difference between a program designed to run well on an MCU and a program written quickly. At the end of the day, I will also argue that the mindset you have in this manner will force you to avoid JavaScript as the language of choice. JavaScript will, after all, hide a lot of details from you, the programmer, causing you to lose control over exactly what is going on, and if you want a function to run in less than 500 cycles due to timing concerns, you can't really afford JavaScript suddenly running a few milliseconds worth of garbage collection for some non-obvious reason at some point. The language of choice for lower level programming is of course therefore usually C, as it has very few and highly predictable hidden operations in it. Well, that said, we are indeed using a lot of C++ at my workplace, and I'm of very ambivalent comfort with that, because we are paying some extra overhead for it. But language aside, I will claim that the mindset is far more important than the language itself. So let's talk a little bit about the constraints you want to keep in the back of your mind while programming. That is for being the memory, the performance, the code size, and the power. And let's go into all of those in detail, shall we? The biggest constraint of an MCU is obviously the performance. An MCU is weaker, but not bad. Importantly, the biggest gains you'll find is on the algorithmic levels, whereas a PC program could easily iterate over 1 million elements in an array to find the one it needs and not break a sweat while doing so. The MCU program would want to avoid doing such an operation, typically by picking a better data structure not needing that linear search. There is generally always an option to do an algorithmic space-time trade-off, meaning you can find an algorithm that does the thing you want to do using less work. In the million elements lookup example, you can use a data structure that returns an element without doing that O of n search, say a hash map, returning you the element in O of log n search time instead. You can also tell the compiler that performance is the critical aspect of your application, and that any trade-off it does should assist performance rather than anything else. This is the classic -03 flag, aka optimize for performance no matter what the cost mode. It typically creates far larger code than you would with the more conservative -02 flag. If you really want to get down to it, you may also need to look at the instruction levels yourself. A former coworker of mine used to write tech demos for the Game Boy Advance. If he wanted to run content at 60 FPS on the Game Boy, the MCU of that platform allowed some 5 instructions per pixel, and that wasn't a lot. And in fact, it sounds awfully limiting, but it's amazing what you can really achieve in 5 cycles per pixel just by moving some of the heavier calculations out of a tight inner loop and pre-calculating some stuff upfront. The biggest low-level reason for instructions taking a while is memory operations. While an add instruction can be done in a cycle, a load operation typically takes 100 cycles or 200 cycles, and doing those in an inner loop is always going to slow you down. Being able to identify that your inner loop is doing memory operations and to be able to avoid doing that is where you'll find a lot of performance, and this is essentially what optimization is all about. You should also be aware that function calls in C has a genuine cost to them. This is true for all languages, by the way. It's just that other languages than C tend to never get to the point where that is the significant bottleneck. So eliminating the overhead of function calls has various solutions to them. The big one is link time optimizations, which try to avoid calling function overheads at all, but it's barely working in my opinion. You can inline functions, which allows compilers to get rid of that. Static functions have less of a cost to them because the compiler knows that they are from the same file and therefore can avoid some of the heavier function call overheads. And there's also macro functions, which used to be done a lot because it kind of bypassed the compiler, but isn't really that much needed anymore. The key point here is nonetheless, optimizing randomly is meaningless. You want to keep it in the back of your mind that you want to write optimal performant applications, but you want to use a profiler to identify hotspots and figure out how to optimize those hotspots separately. In my biased opinion, power is probably more important than performance. We can always make hardware or software that is faster by just increasing the clock speed of the MCU it's running on. The only thing preventing us from doing so is the power budget. If you use more power than you can dissipate heat, the MCU will literally burn, and this is especially important for mobile devices. You don't want a cell phone that is literally too hot to handle. Some MCUs come with DVFS, that's Dynamic Voltage Frequency Scaling. This is a concept where you have some controller deciding the frequency of the MCU, and input to this controller typically includes the current temperature of the MCU, but also often how often the chip is used, as on usage uptime. There's actually two types of MCUs out there. You got the MCUs that's always off. The Autopass chip in a car is a great example of this. Every few seconds it wakes up to listen if there's a radio signal from a toll road station nearby. If there is, it will start communicating with that, but more typically it will just go back to sleep because there wasn't any. By this design, the Autopass chip uses so little battery that the chip is likely to be obsolete long before the battery on it is dead. And that's awesome. Now, by comparison, you got the always-on MCUs. These are MCUs that's constantly doing something, you never turn them off. The traction control controller of a car is a great example. It's responsible for detecting if your car is sliding along the road and apply brakes if you are. And you don't want to turn that off. You want that to check this as frequently as possible, because the more times it checks this per second, the less latency you have before it starts doing something about the situation. So you never turn this off unless you actually park your car. Your cell phone is a bit of both worlds. If you're playing Angry Birds on your phone, it's in always on mode. It's busy generating 60 FPS worth of gameplay, and it's not really sleeping. But it's also using a lot of battery, and you've all seen that. You run out of battery really quick if you open a game on your phone. While on the other hand, if you have it in your pocket, it's in the always off mode. It's sleeping. You don't want it to do anything. You want it to last for 2 weeks if you could. And the only thing that actually uses power at this point is the part of the phone that's actually listening in on incoming calls. Of course, if you have Facebook app also running, that Facebook app will wake up once every second and check if there's been any activity, and it does so by going online and checking your internet Facebook feed. And this is really expensive, and you've all seen the Facebook app being in the news eating power. That's why it's power hungry. It's waking the phone up. In the top right of the slide here, you can see the power usage formula of an MCU. It's basically the sum of the dynamic power, which is the power cost of toggling a transistor from 0 to 1 or back. And this is quite substantial, but it really only applies in the very small window of time when some transistor is actually toggling. You also got the short circuit power, which is what you get when a hardware is connecting a 0 and a 1 wire, and normally that shouldn't happen, but while transitioning from a 0 to 1, that actually happens quite a bit. And it's really hard to model, and it's usually therefore just multiplied into the dynamic cost of transistor toggling. We usually therefore often ignore it. And finally, you got the static leakage cost. This is the cost of keeping a transistor always on and off in most transistor technologies. The cost of doing so is far lower than the dynamic power toggle usage, but it's the notable part when you're doing nothing in a chip. To reduce this power consumption, you could turn off large parts of your chip. Say if you don't use the Wi-Fi, you just turn off that part and it's not even using any power. The cost of turning those parts off is, unfortunately, that turning them back on again involves a lot of transistor initialization, which is basically again dynamic power, and also a lot of time because initializing hardware takes a little while. So, looking at the always off type of system on the leftmost hand of the slide here, The only real cost is leakage, because there's not much going on in the system. At best, you may have a clock counter increasing every millisecond. If you want to reduce the power consumption of this system, you want to avoid doing what the Facebook app is doing. You want to avoid waking up. So if you can wake up less, you will allow the parts of the hardware that can go to sleep to stay asleep, and this is what you can do to maximize the power usage. So if you're ever writing a Facebook app, don't wake up every second. Wake up every 5 minutes. It's fine, people can wait. If you're really careful, you can check maybe the next minute after receiving a message or sending a message every second. By comparison, you got the always on chip. This is when you're running Angry Birds. In this world, the dynamic power usage far outweighs the leakage power usage. So it's really the only thing we need to care about. The dynamic power usage is at the bottom of the slide, given here as a capacitance, which is just a factor of all the transistors, multiplied by the voltage squared multiplied by the frequency. As it happens, the voltage is a function of the frequency. If you increase the frequency, you have to increase the voltage, otherwise you get errors in your calculations. So you can think of the voltage as a function of frequency, and therefore the dynamic power is kind of like a constant multiplied by the frequency cubed. Kind of. I'm simplifying a lot here. But I'm trying to say here that increasing the frequency has a substantial impact on power usage in an always-on system. To reduce power usage, you want to reduce the frequency. It's that easy. But by reducing the frequency, you're also taking longer time to run. In the case of the Angry Birds game, you don't want your per frame CPU workload to take more than one frame. So if the Angry Birds game is expecting to run 60 frames per second, the CPU workload needs to be done in less than the 60th of a second. So if you can achieve that, great, we can reduce the clock frequency until the CPU workload is just short of a 60th of a second. And you can, in the ideal world, configure your DVFS system to take that workload as some input and scale the frequency down accordingly. And this makes a substantial impact on power usage. Reducing the power is really all about increasing the performance and vice versa, in my opinion. You may not agree, it also depends a little bit on what kind of platform you're working on. I'm obviously biased by working in a mobile world where everything is handheld and the power budgets are very, very constrained. A frequently overlooked constraint is the storage constraints. A hard drive these days usually holds in the size of terabytes of storage capacity, but your MCU doesn't come with one. Instead, your MCU typically comes with a ROM chip, which can hold somewhere in the range of a few hundred kilobytes of storage to maybe a few megabytes if you're lucky. If you want to fit your binary and the data your binaries need and any support libraries and possibly even an operating system onto that storage, you may have a problem. And getting around the constraints that your output code need to fit into this small little ROM chip is a challenge at times. You can tell your compiler to help you out by optimizing your code for size. That's the -o lowercase s flag. This will generate smaller code, yes, but also code that frequently runs slower, so it may not even be a great trade-off. What you can do is strip your binaries. That will remove unused code that's not called anywhere, and also segments of your code that's not actually useful, like a GPL license if you compile with the GCC. Programming with these limits in mind is constraining, absolutely, but it's possible to work around them. The key points of tricks to do is that you want to store your data efficiently. Maybe you can generate data based on very small input seeds rather than loading full data. You may not need to store a full texture if you can just generate the texture up front. You can also abuse what libraries you have available and remove the libraries you don't actually need. And a surprising amount of stuff you can actually do without. In the operating system section, there's also the problem of the embedded OS. An operating system is a huge beast, and these won't fit on your MCU ROM. So we have embedded operating systems, which are lightweight versions of operating systems that are designed to fit. And these are written with the size constraints and other constraints we've talked about. And as a result, they usually come with very limited functionality. You usually don't have thread support. You usually only support one process in the entire system. You typically don't have advanced OS functionality like memory protection and swap disk. I mean, you don't even have a hard drive to swap to. Mutexes or other conveniences that programmers take for granted in a desktop environment. You may not have those. Now, even as limited as the embedded OS is, they do add to that storage size constraint, and also they take up space in ROM. So the question is, do you even need one? You have an option to just forgo all the operating system setups and just run as a bare metal driver, a bare metal application. The problem in doing so is that you don't get any OS support, so any drivers and stuff like that, you have to write them yourself if you want them. And if you want any interrupt handling, you have to write your own interrupt handler. In fact, you probably need to, otherwise you can't receive any signals from hardware. But it's an option. Bare metal, as you call it when you don't run with an OS, give you that extra bit of storage space, which is great if you're really storage constrained, and a lot of MCUs do run bare metal just because it's simpler. Finally, we have memory constraints. I've been blessed to not work with any platforms where memory has been a significant constraint, but you may not be so lucky. Where a PC typically has RAM sized in the gigabytes, an MCU has less. If you're really unlucky, in the kilobytes, though that usually isn't the case anymore. Making most of the RAM you have can be a genuine challenge when writing low-level code. I want to again note that the algorithmic trade-off is possible. You can almost always pay more CPU processing in return for using less RAM, and whether that is an acceptable trade or not is up to you as a programmer. Some platforms also store instructions in RAM instead of ROM. When they do, there is obviously less RAM to go around for everything else, so your binary footprint may really matter in this situation as it leaves less RAM for the application itself. But when they don't, you can often put constants in code that is available through ROM, which then opens up more RAM for you. Also, recursion. It's an academic endeavor that's interesting, but as things often go in real life, less useful. Recursion typically adds a stack cost to it, and that stack cost can be quite substantial, and therefore not an option in a RAM-constrained environment. I would generally avoid recursion in any industry code I ever review. So, if you really want to make an impact on memory usage, you need to pay attention to your variable types. So let's do some examples on that. I promised an example. Here you see a data structure foo containing 4 member variables of various data types. The question is, how big is this data structure in RAM? And let's assume a 32-bit data type environment. In this world, you'd be surprised thinking that you can take 1 byte plus 2 times 4 bytes plus 8 bytes plus 1 byte and add them up to 18 bytes, and that's the size of the data structure. And this is how it would indeed work in the sane world, but it's not how it works on your computer. The problem is because the CPU load store operations have alignment limitations. They can only read an integer at the 4-byte boundary. So if you want to load an integer, that integer must be stored at an address divisible by 4. If you want to load an 8-byte double, you need to load that at an address divisible by 8. And this means that the layout of our data structure is a bit of an annoyance, because yeah, I can put my A up here, that's not a problem, but the next member, B, is then requiring to be at the 4 aligned boundary, which is leaving 3 small holes in my data structure. And again, C must be at an 8 aligned address, so that leaves 4 holes in my data structure here. And yeah, sure, D can follow immediately after C because it's a 1-byte data type, meaning it has a 1-byte address requirement. But then we have to add another 7 bytes worth of data in here. Again, dummy data. It's not actually useful for anything. Why? Well, the thing is, there's nothing preventing us from making an array of this structure. And if we do, we need to ensure that each element of this array has a starting address that is aligned to the largest data type, in this case the double. So the size of this data structure is 32 bytes. That's substantial. It would be easier if we could rewrite the data structure and reorder their appearance. And if you're just adding variables in a local stack in C, the compiler will certainly do so, but for a data structure it can't, because that data structure is an interface. The interfaces need to work across multiple program modules. So you need to ensure that they're in the same order in every module. So if we rearrange them a little bit ourselves, we can certainly cut down on the memory size of this data structure. Here's a minimal set. Now, we still waste 2 bytes this way, and it's actually possible to make this even smaller. We can make it 18 bytes instead of the 20 it was in the previous slide. The way to do that is to declare this data structure as packed. What that means is that your compiler will assume that all of these data types are placed at unaligned addresses. So when loading this double C, it doesn't do one 8-byte memory load. It does 8 1-byte memory loads and shifts them together into an 8-byte value. This works at any alignment, but instead of doing 1 memory transaction to load my member C, I now do 8 memory transactions to load my memory C, and I have to pay for a lot of bit operations to build that resulting data structure. So packed has a real cost in performance. I would not use them unless you really know what you're doing. The only actual use case for a packed data structure, in my opinion, is when you have a file input that needs to be loaded. That's slow anyway.